Thank you. Thank you for that introduction, Anna. And as much as I would love to talk about any one of those research areas, and you see my email address, you can ask me later by email about any of those topics. Today, I want to talk to you about a framework that my colleagues and I, in teaching an introductory course in data science, have developed to kind of frame data science so that whatever new kind of analytic approaches come out, and they're developed all the time and being developed as we speak, then we have a scaffolding, and this is providing that for you to be able to know what the appropriate statistical technique is, or analytic technique is, for you to choose in data science. So we're going to talk briefly about why data science evolved. What was the need for data science? Why did it become a discipline? Then go into a general description of this framework for understanding analytic approaches in data science. Finally, we're going to use various different analytic approaches. We're not going to go through all of them. We don't have that much time, but go over major analytic approaches and use the framework to illustrate vis-a-vis those analytic approaches how you can use that framework to identify what the appropriate technique is. And then we will actually have some time in the latter hour of this session to be able to practice, where you guys will get into groups and actually practice solving problems in data science, or at least figuring out how you might solve those problems in data science. Specifically, what analytic technique would you choose given the problem and given the data you think you might have given that problem. So without further ado, we will jump in to understand why we even have data science as a field. So the field of data science came out of an exciting opportunity / problem that is represented by big data. So we have this huge influx of data that scientists did not have access to before. Before big data, there was reasonably small data sets. There were not, thousands and thousands upon thousands of, data entries and many cases or people or participants in these data sets. And so data science arose out of this need for being able to bring to the table different kinds of approaches to analyze big data. Now, data science isn't limited to big data. We're also going to talk about analysis of smaller data sets, because that is something that data scientists do as well. But in addition to, like, statisticians being able to, analyze small data sets, data scientists are able to analyze big data, and they bring to the table of real-world problems with complex data sets a litany of different tools, and their job is to not only do the analyses, but choose the right analytic approach. So as a primer for becoming a data scientist, or giving you a framework if you're beginning to be a data scientist, for trying to make sense of all those different analytic approaches, we're going to go forward and I'm going to give you examples from the microcosm of individual human behavior to the macrocosm of the entire natural world and celestial bodies, to try to illustrate this need for data science. So starting with something that, we have big data sets from individual human behavior, that comes down to our cell phones and other kinds of devices that we have, mobile devices. That those serve as a great example of the kind of big data that is now available for the behavioral sciences. That's very different than what it looked like to be a behavioral scientist before the invent of big data. Before the invent of big data, behavioral scientists would collect data in small scale studies. They might go into it with a specific hypothesis based on theory, or they might just have some small scale data and do whatever statistical analysis was appropriate for their data, which we'll go over. But now with big data, we analyze that using computational approaches that were developed because of this opportunity that we had, or are at least being utilized because of the opportunity that we had with this big data in behavioral science. Similar thing has occurred in the transition in natural sciences. So originally biology and other natural sciences would, collect small studies in the wild, and people would have to sit in, observation huts or tents and observe, natural phenomenon, or go and take individual readings of individual creeks. Now, with the advent of sensors and large international and national databases where all of the sensors are collecting ongoing at all time, and natural scientists, earth scientists can actually access these, the life of a earth scientist or biologist or other natural scientist has changed very much to using very different methodological approaches, but also analytic approaches. So with all this change, there still exists the old approaches and the new approaches. So how do we make sense of them all? How do we frame them all? And now I'm going to provide an overview of our framework for data science, which gives you some concepts to be able to understand what are these different analytic approaches doing and why. And so I want to start with the idea that we needed to expand the concept of what science is with this invent of big data, with the change in how science is done. Science isn't just the scientific method the way that we thought of it for, hundreds of years. That is still part of science. I take a bit of an argument for this Wired magazine article, is that we still do scientific research a la the scientific method, but now we also do research based on large data sets, these big data sets that we have access to, where we didn't go into them with a theory and then derive a hypothesis and therefore go collect data. We didn't follow the traditional scientific method. We have this data and now we have to make sense of it. Therefore, scholars in data science have identified that there are now two approaches to doing scientific research. And that is a contrast of the old way, top-down, theory-driven approach, where you went in, from the beginning of science to, I have a theory and I'm going to derive a hypothesis from that, and then I'm going to test it. And then I'll tell you about the other approach that we have developed out of this, availability of data that wasn't theory-driven. So first, let's start with this top-down or theory-driven research. Give you one of the classic examples is the theory that some of the oldest forefathers of science had in behavioral science. He presupposed that prayer works. That was his hypothesis, is that prayer works, and then came up with a hypothesis to test the theory that prayer works. And that hypothesis was that people who are prayed more for should live longer. And then he went into identifying a method of studying that. He identified that people who are prayed more for would be the royals, the ruling body, and then knights, and then clergymen, and then everybody else. And so those royals should live longer than, all these other levels. And he got the data for this, and actually the data did not support the conclusion. The opposite was true. Due to a number of reasons we understand now, this meant that the hypothesis was not supporting the theory. In contrast to this theory-driven top-down approach that we've carried on since these early studies, we now have a ground-up or data-driven approach where we have these big data sets that tell us about how large processes work, more than just a single hypothesis, and I'm going to collect some data that can test that hypothesis. But these large scale data sets are more difficult to make sense of. Very clear cut when we have top down theory driven research, we either support the hypothesis or we fail to support our hypothesis. We have to, we'll talk a little bit about null hypothesis significance testing. I won't go into detail, but the idea is you reject the null hypothesis, and then you have your decision based on the outcome of your statistical analysis. It's much more complex when we do ground up data-driven research to try to conclude something from that. And you'll see examples of that as we go forward. So to put a fine point on it, the logic behind top-down theory-driven research is different than the logic behind bottom-up or data-driven research. Top-down theory-driven research uses the logical inference process of deduction. You use a theory to make hypotheses, as illustrated by the theory that prayer works making that hypothesis, predicting what outcomes you'd find about the correlation between, status and longevity, which are tested and can either be supported or refuted. In that case, refuted. So in this case, this inferential process is going from general, a theory, to specific, a hypothesis and actual outcomes that you expect to have in your scientific study, from theory to hypothesis. So an example of deduction is that I work at USC. I might have the theory that USC students are hardworking. And the way that I would then try to observe that is look at the student in my class and say, is this student hardworking? And that would either support or not support the theory. In contrast, induction goes the other way. When you think of induction and inductive reasoning, think about Sherlock Holmes. Yes, he used deduction, but he was most famous for induction, where he would look at how far the parsley melted into the butter and come up with a theory from that. So inductive reasoning, uses observations to infer general rules. It goes from specific to general. Here we look at the data and we try to derive models or rules from the data. We go from observation to theory. The example, when we're talking about my USC students, the way that this reasoning would work in that case is I would observe the students in my class are very hardworking. And then I would make the theory or the model that USC students in general are hardworking. So we're going to see these different kinds of reasoning and logic follow through to help us determine what kind of research we're doing and why in terms of the analytic approaches. Top-down approaches use deductive reasoning, and they're going to use certain kind of analytic approaches. Bottom-up research uses induction, and you'll see that the analytic approaches follow that. One additional note that is supportive and further helps us to refine our understanding of these approaches and where they fit is that data science is known. This isn't my observation. This is a known perspective on what data science is. Data science is claimed from many data scientists to be the intersection of computational methods, coding, statistical analyses, basic statistics, and application domains. Data science is in the middle. And as data scientists, we learn how to do computational approaches like the ones I'll talk about. We also learn how to pull from the statistical approaches that are with us from the early days of theory-driven research that I alluded to earlier. And we use any analytic approach from either side or both sides of the upper Venn diagram and apply it to solve a problem in a specific domain. And that means sometimes if we have a domain that has a unique kind of data, sometimes we're either creating, new analytic approaches, new computational methods for our kind of data, or searching beyond the basics to other computational approaches that, researchers in computer science have developed and adopting them and bringing them into data science for the kind of data that we have in our given application domain, whether that be medicine, marketing, education, lots of different domains of application. So now that you have this high view, overarching, overall scaffold of understanding how we're going to organize data science, I'm now going to give you some of the pieces. Now, these are just the most popular pieces, the most well-known pieces, and a few additional examples. There are many, many, many different types of analysis in data science. I'm just giving you the very basics, the very introduction to this. But what we're going to do is we're going to reference back to that scaffold. We're going to reference back to the framework and show how these common, ubiquitous pieces that are across many different domains being used, how they fit in our scaffold, so that then as you learn about other kinds of approaches, you can figure out where these new approaches fit that you learn about. So the first question is, what type of data do you have? Now, there are lots of types of data. I'll briefly mention some other ones when I allude to other kinds of approaches that are common. We won't go into all the specifics of different kinds of data, but know that there are lots of kinds of data out there, and then there are therefore lots of kinds of statistical or analytic approaches that are used. But we're going to spend most of our time talking about tabular data because tabular data is the most common. This is what we think of as data. This is what we think of spreadsheets, and there's rows and columns with a bunch of numbers in them, and sometimes letters or words. That is tabular data, and tabular data is the most ubiquitous, and therefore we're going to concentrate most on, and indeed the most common and prolific approaches are useful for tabular data. So we're going to spend most of our time and just share with you some examples of other kinds of data beyond that. So if you have tabular data, you'll probably know it. It looks like what you think data should look like. There's columns, there's rows, and what these columns and rows contain depend on a number of factors, and they help us determine what we're going to do. Now, it goes back to, how did you get this data? This theory-driven versus data-driven, top-down versus bottom-up, indicates how you got this data. Did you get this data because you set out, you had a theory, you derived some hypotheses, and then you ran a study with a sample of people to get this data? That is going to imply potentially different kinds of analytic approaches, because you already know what your relationship you're interested in, and your goal is to identify, does that relationship exist, in order to be able to determine whether your hypothesis and therefore your theory was supported or not. Or do you have a larger data set that wasn't developed in that way? Maybe it was just a data-driven approach where you got some data, and now you're going to see what the data tells you. So in both cases, we can think of tabular data as having independent variables and dependent variables. These are terms adopted from the theory-driven top-down approach. And when we get there and talk about those analytic approaches, you'll see this terminology again. But it's a general sense that sometimes you have predictor variables, independent variables, the ones that you think are going to help you determine your outcome, and then your dependent variable, the variable that you think is your outcome. Now, in theory-driven top-down research, these are very important to identify, because your research question, like, does prayer work? That theory derives the hypothesis that there should be a relationship, a positive relationship, between status and longevity. Independent variable would be status, and your dependent variable would be longevity. So for those, it becomes very important which is which. In top theory-driven data-driven bottom-up research, we don't call them independent and dependent variables, but this distinction between predictor and outcome is also important, as you'll see in a minute. Also, it's important to note whether your variables are categorical or continuous, because the specific nuances of exactly what analysis you're going to do within a category of analyses is going to be determined by that. So categorical is when you can't put things in order, like gender identities. those are not able to put in order. They're groups, they're categories. Car types, you know, makes or models of cars, they can't be put in order. They're just categories. Whereas continuous variables like age can be put in order. Score on an exam can be put in order. If you think continuous, think continuum, the idea that they can be put in order. So we'll come back to that idea that classification, our first example of a theory or a bottom-up data-driven approach that we're going to talk about, that is one of the most common computational approaches. If you walk away knowing something about data science, I hope you learn about classification, because it's the crux of much of what is done in data science and computer science these days. And so here, there's both going to be the possibility for categorical and continuous variables, and I'll talk about that in a minute. But the outcome, the one thing we're trying to predict in classification, it's not called a dependent variable or a outcome. It's called that you have classes. So this is inherently categorical. Class, like category, is either or. You can see on the image there, you know, triangle or circle. Those is labeled as a class. And what you'll have in classification, when you can do classification when it's possible, is you have a bunch of instances. These are cases, people, individuals, whatever your row is in your data set, those are your instances. And the number of rows you have in your data set is the number of instances. Here in this diagram, it's people. People that can either be labeled as a circle or a square. And those instances are therefore examples of each of the classes, target and non-target, circle or square. And so what we then do with classification ultimately is we generate a model, as you can see there by that blue line, that when given a new instance, so I have a new person and I have some information about that person, like what degree they have, you know, and their age, and it will help us determine whether they're a circle or a square. So the goal of classification is prediction, predicting whether a new instance, one that we don't know what label it has, based on data that is labeled, that we know what class it belongs to, we use the information about the new instance to try to predict what class it will be in. So in my work, we've done this with huge data sets of individuals experiencing depression or not, or PTSD or not, and we're able to predict if they're distressed or not. If we get a new person come in, gather their data, we can predict whether they're experiencing psychological distress or not. The classic example, though, is a different one. It's about mushrooms. Now, the Audubon guide or any of these kind of books provide an example of the kind of data we would have about an instance. Here, each type of mushroom is an instance, and the label that we want to give the mushroom is whether it's edible or poisonous. This book, of course, identifies for every mushroom whether it's edible or poisonous. And then unknown edibility, we probably, I don't know what we want to do with those, probably just assume they're poisonous. But the goal then is, imagine you have a new mushroom. It's not in the book. What are you going to do? Can you eat it or not? Well, personally, I wouldn't eat it. But if you're trying to predict whether it's safe to eat or not from the data, that is a classification problem. And therefore, you're using the data that you have, as an example is in this book, making that data into tabular data. And all of the mushrooms need to be identified as having the label of poisonous or edible. And ultimately, with this new mushroom, we would be able to use what we know about the new mushroom to predict whether it would be poisonous or edible. So here are examples of the different features. These features are the same thing as independent variables. They are predictor variables. Here, all of these features in the mushroom book are all categorical. They're not in a continuum like veil color, as you can see. brown, orange, white, yellow, those are categories. Those are not anything you put into an order. So these are discrete or categorical feature values that every mushroom in the book will have a score for each of these 22 different features, or truly they're just independent variables or predictor variables. So here is our data set. Here's our tabular data set. Most importantly, to be able to do classification, you have to know the class, the thing you want to predict ultimately about that new instance. In this case, our class is poisonous or edible, and we need to know that for each of our instances. And so that's ultimately our outcome variable, the one we want to predict based on all these other 22 other variables that in this case are categorical. They could be continuous though in classification. They don't have to be categorical. They could be numbers. They could be, something that's continuous. So that's the difference between, discrete and continuous classification. These are two types of classification, but ultimately you're trying to predict the label, which is a categorical, either poisonous or edible, of a new instance that you would have, one that you've never seen before. A new person that might be depressed or not, a new mushroom that might be edible or not, a new person that might be a circle or a square, or circle or triangle, excuse me. So I do want to make a note. I'm not going to go into the different algorithms that can be used to do this classification problem because there are far too many to explain at this point. I do want to demystify a little bit though. So there's lots of different ways, mathematical computational ways of doing this. Logistic regression, naive Bayes classifier, support vector machine, decision tree, random forest, kernel methods, neural networks, and this big scary word, deep learning. Deep learning is actually evidenced here as there's a diagram, but it's doing the same thing that you'd be doing. You have this set of animals in this case that you're trying to classify into dogs and cats and neither, and you have a new instance and you label it as a cat. It's just that there's many layers of neural networks in what a deep learning algorithm is doing. It does it in multiple pieces. It reruns a neural network, which is a neural network is just another type of algorithm that does classification. It just does it in an iterative fashion. It's not, it is very exciting, and I don't mean to belittle it, but when you hear the word deep learning, you don't need to be scared. It's just another analytic approach, often used for classification, although it can be used for other kinds of analytic approaches as well. So this is to remind ourselves, I inferred at the beginning that this is a inductive approach, a bottom-up approach, that we have these observations and we want to create a model. We want to create a rule that will then, when we have new data, we can use that rule, we can use that algorithm to then predict whether the new instance applies to the one class or the other class, or if we have more than two classes, a third class. So remember that induction, like Sherlock Holmes, uses observation to infer general rules. It's one of these bottom-up data-driven approaches. And classifiers indeed use induction. They generate this model about the classes from the data. And then you use deduction to make a inference about the new data, but ultimately the crux of creating a classifier is to use induction. It's to make a model based on the data, a data-driven approach that then can be used to make new predictions. So I do want to point out that classification is broader than that. It can be used with other kinds of data too, not just tabular data. It's very commonly used with tabular data, but it is also can be used with text data, for example. Now, I want to provide another common analytic approach. This is another data-driven bottom-up approach, and it is clustering. Clustering is something that you can do when you don't have labels. Remember, label was what class each of the instances fell into. Here, we don't have a specific class that we want to try to predict whether an instance falls into or not. What we want is the algorithm to just make sense of the data for us and put it into groups. It's like just asking the data, the analytic approach. Hey, tell me what you see in the data given all of these variables. And so in this case, there is no distinction between independent variable and dependent variable, or class and feature. We call all of the variables features. They're not independent variable and dependent variable. They're just all variables. And ultimately, we can give that data, still tabular data, to a clustering algorithm. And we can also define for it, or not, it's an option, the number of clusters or groups that we want. And what the clustering algorithm will do is find the best assignment of instances to the clusters. So it'll find the best way of organizing the data into groups by some optimization criteria. Just like classification, there's lots of them. I could list them off for you. There's no need. It's just an illustration of that there's lots of different actual algorithms for defining and mathematically defining what the best way of identifying these clusters are. And ultimately, the clusters just represent similar instances. They're groupings of data. And I'll give you an example of this. So this is an example from real research that's been done with kids who are coming into a ICU and getting much poorer in health versus other kids that weren't declining in health when they came in for respiratory issues to this child ICU. And so what they really wanted to do is take all this sensor data. See that little baby there? He is covered in sensors to be able to collect all this data. And they didn't know what it was to predict. They just wanted to know what differentiated these children into these clusters of sick versus healthier children in the ICU. And they let the algorithm do its thing, and they identified these two clusters, which indeed did map onto sick versus healthier kids. The ones that got really sick and might die, and the kids that didn't get so sick and didn't die. So what we do is we find the clusters, and then we try to understand the clusters with support of experts in the domain. Remember that bottom circle is in the domain? Data scientists don't work in a bubble. They work with domain experts. Here in this case, it was pediatric specialists and respiratory specialists to try to help them make sense of the data, these two clusters, so that they go, now I know why the kids are getting sick. And since they learn what comes with being more likely to die than not, what distinguishes these two clusters from each other, so that then methods and remedial actions could be taken to try to make sure all of the kids made it through, and that there wasn't this problem that was occurring among the high mortality cluster, to prevent that issue. So this is a success story in data science, but they didn't go in knowing who was going to get sick and who wasn't. They didn't know this kid was going to get sick. They wanted to just understand the data as it was evolving in this very large data set that they had. So one note about this is that these two types of learning, machine learning, not your learning, the machine's learning, are basically clustered into two types. Now, there are ones in between these, but supervised learning is when training data labeled by humans, they're providing annotations to help the machine learn, because they have a specific thing they want the machine to learn, like identifying mushrooms that are poisonous versus edible. So the class, when a person has to provide the data, whether a class is a circle or a triangle, or whether they're depressed or not, that's called supervised learning. So these cases of classification are supervised learning. Clustering, in contrast, is unsupervised learning. Remember, there's no class, there's no independent variable and dependent variable, there's no predictor versus outcome, they're all just variables. And so there's not any special labeled annotated data to try to teach the algorithm what we want it to learn. We just let it run and then try to make sense of it. So 2 points quickly. One is that there is a range. There's semi-supervised learning, which is in the middle, and there can be, the fully supervised and super unsupervised, and there is, gray space in between. So these are categories, but they're also a bit continuous. And then it's important to think of this as what the resources you need too. Supervised learning is more costly because you have to have somebody saying this person is depressed, this person's not depressed. Getting that kind of labeled data can be very expensive. So there's all practical considerations when choosing your approach as well. Now, we're switching the other way. We're going top down. We're now going to talk about deduction. I mentioned earlier about null hypothesis significance testing and how that's the old way of doing things when you have a theory-driven research. So indeed, as promised, null hypothesis significance testing uses deduction. This is the example of does prayer work? You make a specific hypothesis, which is tested using the approach of null hypothesis significance testing. So null hypothesis significance testing in formal terms is the scientific method of deciding when an outcome of a study, results from a sample, support a particular theory or not. So if we had the entire population, we wouldn't need to do this. We would know the answer. But we take a sample because we very rarely, if ever, have all the data from the entire population. So we take a sample and we then use statistical approaches to try to analyze the data, that then we draw conclusions about the larger population from that sample. So here is really where it's important to identify your independent variable and your dependent variable, and also whether each of those is categorical or continuous. And we're going to run a basic statistical analysis on the sample and make conclusions about the population based on the results of that analysis. And we're choosing it based on the independent variable and the dependent variable and whether they're categorical or continuous. And what you're ultimately going to do is you run that statistical test, whatever statistical test it is. It's likely, if you're using traditional null hypothesis significance testing, it's going to give you a p-value. That p-value is the probability that you're saying there is an effect when there is not one. So it's a probability of a false positive. Probability you say, aha, I found a relationship, when in fact no relationship really exists in the population. Because remember, we just have a sample. So we're making a conclusion about the population. So what's true in the population we'll never know. And the p-value is the likelihood that we're wrong if we say, aha, we do have an effect, a relationship between the independent variable and the dependent variable. So statistically, this p-value has to be less than 0.05. Why? Because our scientific forebears declared it to be so. They determined that 5 times out of 100 was okay for there to be a false positive, that was an acceptable level. So that if your p-value in your result from your study, like, running the analysis with the, the longevity and status, if that p-value was less than 0.05, whatever statistical analysis, actually that would be a correlation that you would run, because both of those are continuous variables. If that correlation, the significance, the p-value for that correlation was less than 0.05, you would say, I can conclude something. Status, maybe it's not, maybe it's categorical, then I would have to choose an ANOVA. Unfortunately, I don't have time to go over all of these, but come back to me, take a screenshot. This is the way you choose the general category of statistical approaches that you're going to run to get your p-value that helps you. Again, it's just like choosing dichotomous versus or discrete versus continuous classifying depending on if your features are continuous or categorical. And same thing here, we're choosing based on whether our independent variable or independent variables, sometimes we have more than one, are continuous or categorical, and whether our dependent variable is continuous or categorical. That helps us choose the right statistical approach, specific null hypothesis significance test to do, correlation, regression, t-test, ANOVA, logistical regression, chi-square test, or log linear. Those are chosen based on this chart, and I would walk through it if we had a little more time, but you can always find out this information on the internet or ask me. You have my email address. So what if you don't have any data yet? We talked about tabular data, the most popular data. Now we're talking about non-existence of data. And that is what happens when we have simulated data, when we don't have access to real data and we create simulations. That is an opportunity if we don't have any data yet. Simulation is also a theory-driven approach, just like null hypothesis significance testing. But here we create a mathematical model of the phenomenon that we're trying to predict, make a prediction based on that model, and then when the thing happens in the world and we have observed data, when the event occurs, we can compare our prediction from our simulation to the observed data and say, do they match? So let me give you a couple examples. So traffic, there are simulations of traffic. So you can have a mathematical model for traffic flow patterns, and you might have a prediction based on if there's an accident or construction right here. And then when accident or construction occurs right there, then you can observe what happens and compare that to what your model predicted would happen and see how good your model is. If it's accurate, if the prediction matches the reality, then you know your model is very good. If it's really far from what happens, then you know your model was not very good. Similar things can be done for physics models, like airflow over an engine. You would have the prediction of if this got gunked up, what would happen? Gunk it up in a real engine and then see what happens to the airflow. Does that match your prediction? There can be simulations for every kind of thing. Natural models, agricultural models, social models, economic models, infrastructure models, disaster relief. Like there could be a prediction about how many people would stay and go in a natural disaster or a man-made disaster. And ultimately, the goal is that if their variables overlap, that you could have simulation across different disciplines. And this would be, you could predict how much something would cost, like corn would cost, based on atmosphere humidity. Now that's kind of a ways off, but it shows you the opportunities that I have in simulation, even though we don't have data yet, and we ultimately wait to get the observed data, the real data from the real world, to test our simulations and see how accurate they are. So remember, I promised you that there are opportunities for unique kinds of data that you might analyze. You might have social media data. You might have the frequency with which they communicate on a social network, the subgroups that they fall into. You can also have spatial data. This is another kind of data that you might have. Relationships between things in space. GPS units, you use geographic information system, or GIS, to analyze this data often. You can have time series data. Time series has an element of time and how the variables that you're interested in, like here, temperature and rainfall, change over time. It can be represented in tabular form, but there is a key difference between time series data and non-time series tabular data. Here, the correlation or the relationship between my mood and my proximity to marshmallows is not time series. That's, distance to marshmallows and my mood. those variables are not about time. But if instead you looked at the marshmallows consumed over time, and one of your variables is time, like 6 a.m. to 12 a.m., then it would be a time series data, even though either of these data sets could be represented in tabular form. And of course, there's other kinds of data sets. There are text data. There are data that your bank has about, fraudulent credit card alerts and all your purchases. Behavioral data of where you go every day. That might be GPS data combined with your purchases. There's all kinds of data that exists. And there are unique analyses that are created for each of these types of data. For example, there are many different kinds of algorithms for analyzing text data. But I will talk about another category of analytic approaches that cross, just like classification and clustering and statistical methods, that cross types of data and can be used more broadly. And that is when we have patterns. All of those different types of data I just talked about, there are patterns that could be identified. And pattern detection or pattern learning and pattern discovery or pattern mining represent two general approaches, and they illustrate for us a bit of what we talked about early. So let's use these again to identify what we've learned about our scaffold. So first, these are data-driven approaches. These are not theory-driven approaches. These are deriving from the data, bottom up, that we have the data and we want to make inferences about patterns. What we want from the data are patterns. Just like from classification, we want models. We're getting something general from the specific observed data. And just like we talked about classification and clustering being more supervised, one being more unsupervised, pattern detection and learning is more supervised, and pattern discovery and mining is more unsupervised. And we see that in that pattern detection and pattern learning, we annotate, some human has to annotate the data with patterns, whereas in pattern discovery and mining, it's just the data. But what we get differentiates the two as well in terms of how understandable they are. So the output will be matches to a pattern. If we gave all the patterns that could possibly exist and we told pattern detection to find when we observe those patterns, then we find matches to the patterns that we gave it, that we annotated for. Or we could have some data set where we identify where all these instances of the pattern occur, and then give that to the pattern learning algorithm. In pattern discovery and mining, we just give it the data, just like in clustering, and the just like it, clustering spits out a cluster, and we have to make sense of the clusters. Pattern discovery and pattern mining tell us, here's your patterns, and we as data scientists have to make sense of the patterns and what do they mean. So let me give you an illustration to help with this. Think of back to this idea of credit cards, and maybe there's credit card fraud, and a algorithm is trying to be developed to identify credit card fraud when it occurs, so that we can have that alert that I get on my phone that says, oh no, there's credit card fraud, check it and tell me. Or text my husband that there's credit card fraud when it's just me going to a gas station. But anyway. So with pattern detection, what you'd have to give the algorithm is every example of what credit card fraud might look like. A gas station purchase, then another gas station purchase, 3 gas station purchases, a gas station purchase out of the area, gas station purchase, then fast food. Like, you'd have to give it every example for pattern detection. Pattern learning, we help with all the time with our credit card companies. That's when we say, yes, we're annotating the data, that is credit card fraud. And that data goes back and is given to the algorithm. And then it does pattern learning from the data we've given it, said, yes, that is credit card fraud. Now, not every instance of credit card fraud was always caught. And we never tell them up ahead what the pattern looks like. We just give them instances of this is credit card fraud, and it learns what patterns represent credit card fraud. Pattern discovery and mining, We would just give it the data and it will tell us what it might find credit card fraud. It might find impulsive purchases. It might find patterns of, people cheating on each other, and that comes through in the credit card. Who knows what it will find? It could find anything, but we have to make sense of it as data scientists when we get these patterns that we have to figure out what they mean. So we have run over my time for my example that we were gonna do in plenary in as a group. So I want to give you one more example and just run through it. We were going to do this as a brainstorming activity, but in just a few minutes, you're going to get an actual problem that you could analyze using one of these approaches, and you have to come back to me and the rest of the group. In groups, you're going to do this work, and then you come back to the larger group in plenary and tell us what approaches you think should be done. So as an example, I'm going to give you an example of what I'd like you to do. My problem, if I was given a problem, and this is a problem I've given, and I happen to know the answer, is I've been approached by Google, and Google has the problem of their spam emails. How do I figure out if it's a spam or not spam? Well, you could do lots of things. You could do text mining, you could do some, but I'm going to create a classifier. And then as I'm reporting to the group that I chose to do classification to address this problem of determining if it's spam or not, I would then walk through what I learned based on taking this class, if I were a student, and try to identify why it would work well as a classification problem. I would say the classes are spam and not spam. The instances are the emails are the instances. How does an instance get labeled with the class? That's us users, Google users, Gmail users that identify and move it from not spam to spam, or from spam to spam, from inbox to spam. That movement, that's labeling it as spam or not spam, so that then my classifier, my algorithm that's doing classification, has those instances. And there's all kinds of features that I might have. They might be continuous, like what time of day it's sent, what day of the week it's sent. Does it have a discernible sender address? That'd be dichotomous feature. Does it start with to whom this might concern, or ma'am or sir? Things like that would be in my tabular data set, and that's why I think this should be classification. Now, if your problem and your answer to your problem is not classification, you're going to have to talk about different things and help explain why classification, or whatever your approach is the right approach. So here's a little recap. You might want to screen share this for yourself, or take a picture of this with your camera. These are the main approaches that we talked about. So these are the ones that you might choose from to describe to me what approach you're going to choose for the problem that we're going to roll into. And ultimately, what is the goal of it? Unfortunately, I have run out of time to tell you about null hypothesis testing, being able to identify if there's a relationship there, or if you're going to design an experiment. But null hypothesis can be used in either way. And so at this point, I'm going to pop us back out to the group, and Anna and others from Lawrence Livermore are going to help share the slides out. Great. I hope you guys had as productive discussions as it seemed when I hopped in and checked on you. Now we'll have 5 minutes apiece. We'll have my little timer here. And we're going to go through, starting with group 1, then group 2, then group 3, and then we should have, roughly 5 minutes for extra questions or discussion that you guys would like to have. Let's go ahead with group 1, who did the donation problem.
Hi, it was Jessica and I, Kathy, that worked on this problem. And based on the three bullet points under the data section, for the second and third bullet, we didn't have specific information like we didn't know where those profile data are from, like which specific websites. And then the third bullet point, we didn't know which particular social media users they're from. I mean, whether they're Facebook versus TikTok, or other things, or Instagram. So then the only solid data that we can really use is the first bullet, which is the online donations for the last 5 years. So we decided to use the clustering approach. And from that set of data, we want to see of all the donations in the past 5 years, which website or which organization, charity, got the most donations. So we thought up, like, for example, like let's say the breast cancer charity group got the most donations for the last 5 years. If that was the case, then we will start pushing our ads onto that website to see how many of those users are going to donate using the push request or the ad. And then as we get more data there, then we want to kind of push the ads into like a larger group of audience, like maybe for the American Cancer Society, which have, like, they might not, be focused on the breast cancer, but they, might be willing to support breast cancer and donate there. So we would kind of move on from there. And Jessica, do you want to add anything?
No, I think that's pretty much what we talk about. Uh, yeah, so then as we collect more data, then we can decide if there's some other sites that we can include in our ads. Um, yeah.
Great, fantastic. So I'd love to chat with you guys in the time that I have because you left me some time, so I'll fill it.
Yes.
This idea of clustering, it sounds like if what you're clustering are the donors, right? So you would find groups of donors. Is that how you interpret it and what you're talking about? Yeah?
Yes, and then the sites that they most likely to donate.
Ah, I see. So the idea of
Yeah.
like identifying groups of donors, letting the algorithm figure out what are these groups, and then identifying within that group what is the main site. That's a really interesting approach. I like that. I have not heard that one before. Always love to hear a new one. So what would you do hypothetically if all the clusters, because remember, clustering is going to be on a bunch of different variables and it's just putting them all together. What if the most donated site is the same for all of the groups because the algorithm is clustering them based on other similarities, and it just happens to be that then the modal, the most common, is the same across every group.
Um, yeah, I don't know. Then that's the
Yeah.
group that we use.
Yeah, I just wanted to point out about
Right,
clustering is that, if you're letting the algorithm group them, it might not end
right.
up grouping them in the way that is helpful to you. So thinking
Okay.
about other things you can do, you can ask for a different number of clusters that might change and give you more information.
Right.
And then the clusters, if you ask for, five instead of three or four instead of two, or however many you're asking for, that might change your answer, which the answer you're looking for is, let the algorithm typify these people, let it figure out these groups, which is great because it's very data driven and it's just going to tell you what groups exist. But you're also trying to work with it to find a kind of answer that you're looking for. And that's one way that you can do that is, okay, I'm not getting the answer I want. This configuration isn't giving me helpful groups. Maybe asking for a different number of groups might make the groups more helpful to me, giving you out a specific thing you're looking for in those groups. So great work. I love it when I have a new one that I haven't heard before. So thank you guys all, and thank you for the great presentation. We're going to move
Thanks.
on
Thank
to reset the second group, the B problem, another complicated problem. And I love how you guys have all chosen to dive head into these complicated problems. So let's hear from group 2 on the B problem, what their suggestions are.
Yeah, so I'm Corinne, and I worked with Sharon and Vivian on this bee problem. And so the problem here is it appears that bee bites from the Africanized bees have affected tourism. And so we have been tasked to figure out how we could maybe reduce bees so that tourism can thrive again. We chose our output of interest here specifically as bee bites. And this is based on the medical reports that we have available to us over the last 20 years. And so the final analytical approach that we chose is the goal is to reduce the number of bee bites that will hopefully lead to a downstream decision of when might be the best time to travel or visit. We decided to first start off with a pattern analysis using the climate data, population data, other data and pesticide use, and bird population data as well. And we are hoping that from the pattern analysis, we can start to identify and select variables or features that might be important to our predictions. And by then selecting these variables, we can carry out further null hypothesis testing that realistically might take several years. But the goal here is to confirm the variables of interest and to confirm that they are indeed important to our problem. And this might also help us to answer if the cost used for pesticides aligns with its efficacy, or if the alternative method, which is more environmental friendly, of planting crops might appear to be a more feasible idea.
Fantastic. I love your guys' plan. I like that it's a multi-stage and multi-step, and you're kind of using the data-driven approach to kind of get an idea of what might be the best way of handling the problem, and then a theory-driven approach of you guys then have a theory of what you think is driving the problem and what can be done to solve it, and then actually running an experiment where you do null hypothesis significance testing using that theory-driven approach to test it. And yeah, you're right, it might take several years, but I think that's super great that you are layering the different approaches in that way. Yeah, I think I'm very impressed. Some things to consider is that you would need the consent of individuals, because this is medical data. I know you have access to the medical data previously, but if you're going to collect medical data like bee bites going forward in your study where you've manipulated or kind of changed these predictor variables, whatever you find to be from the pattern analysis is predictive, then if you actually then run a study, a theory-driven study, you need to get HIPAA assurances and all those protocols done properly for the medical data from the study going forward. So definitely not a reason not to, but with each of these approaches, we have different considerations. And one of the considerations, across the board is data privacy and making sure we keep the data confidential, but we have additional responsibilities if we're doing null hypothesis significance testing, where we go out and collect new data from a sample. You wouldn't probably get everybody that was on there, but you'd get these sample of people and get the counting the number of bee bites and all that, and you then doing that prospective data analysis with new data. You'd have to make sure you have institutional review approval to do this kind of ongoing studies. So fantastic. Is there anything else you want to say about your solution that has come to mind from my comments?
No, I think that's it. Thank you so much.
Great. Good work again. So Now we will go on and go to the third and final problem, the phishing problem. And I don't mean the swimming kind of fish. I mean the nasty email trap kind of phishing. And group 3 will talk to you about their solution to this also incredibly challenging problem.
All right. Hi, folks. My name is Camille Matthew. I was part of group 3, and let me tell you some of the stuff that we talked about with this issue. As a fun fact, as we were working on this issue, I got a phone call that I didn't recognize the number, and it said likely a scam call. So this is, I'm sure, a very pertinent issue for many folks. So one of the things that we talked about is the first thing we really want to do is figure out what do we know, what do we reasonably know about the issue given the data. So some questions that we were asking ourselves that we would want to determine are what are the common methods and mediums that the scammers are using? Are they tending to use more email, more text, any other, do they have any usage patterns of the tools that they're employing? And then across these instances, which methods are resulting in the highest percentage of successful scams, of successful phishing attempts? We also want to understand who the victims are and if there are any particular demographics, either, you know, related to somebody's, just anything related demographically or maybe even their location. Are there certain groups that are more correlated with successful phishing attempts than others? We also would want to determine a little bit the workflow that the scammers were using. So one of the pieces of data that we have access to in this problem is that there's a record of all interactions with the scammer, taking these interactions and then trying to map out what are the common different events that are occurring within a scammer's workflow, and you know, how frequently are the contacts happening, what's the amount of time between contacts, things like that. And then the last piece is a little bit more familiar perhaps, but any patterns between emails or numbers that are targeted, email domains used by the scammers, grammatical things, anything within the body of a phishing message. When it comes to writing a solution, the approach that we'd like to take there is trying to again identify what is the standard workflow, and how does this impact the action that the victim takes. So what's the final message before the victim acts? What's the average number of messages before that victim acts? Is there any way to tag for you know, requests and emails that are asking for personally identifiable information and things of that nature? Are there any actions that we might be able to compile a list of that the victims are taking? So it costs them on average $1,000. So how, there's got to be a way that that's happening. What are common action buttons that people are including in phishing messages? Tagging language as well, potentially using census data to identify potential victims in the future based on the demographics of the current, is that 100 million, 100 M victims that we have data for. And then finally, determining if there are any ways that we can create rules for things like maybe there's a bizarre contact rule. If somebody has no contacts in country X, could all emails from country X to that person be potential phishing? So ultimately, the way that we talked about this was as a binary classification approach. Basically, for each email received, yes or no, is this potential spam or is this potential phishing? I'm sorry if I'm using the words interchangeably. Ultimately, we want to flag emails based on the identified features of the phishing emails. And then we also want to produce something that could flag emails at any stage of the interaction. So even if something didn't appear to be a phishing email, you know, near the beginning, in context, maybe by the third or fourth layer of an email thread, that could still be flagged for a potential phishing attempt. So that's kind of what we came up with. And I don't know, let me see who else was on. Victoria, I don't know if there's anything you want to add to that.
That pretty much covered all of it in really good detail.
No, that was a very comprehensive approach, and you know, I see definitely how you came down to classification as the ultimate, you know, like tool that you're going to use, but a lot of the other things you talked about implied that there might be ancillary to understand the problem. You might use pattern analysis or, just correlation. Because you talked about your other kind of data that you wanted to understand the bigger picture. And I loved your I want to understand the big picture, and then this is the approach we're going to take. And I know I'm nodding to a few places where you mentioned things, but they definitely made my brain go, well, maybe pattern analysis there, maybe correlation there, maybe this there. So I think that while ultimately, yes, what you want to develop is a classifier when you have all the data streams together and your plan together, ultimately to understand the problem better, like you spent a lot of time talking about, you might want to try other analytic approaches at those preliminary steps too, depending on how they fit what you're trying to do.
That's a great point. Yeah, thank you.
Fantastic work, everybody. I'm so pleased to see what you all shared. Did a great job. Thank you for taking the time, and I hope that gave you some practice. And also, going back to, that framework for data science, the part of the framework that was not mine, that was, larger and already acknowledged within data science of the 3 overlapping circles, that Venn diagram, you got a taste. Yes, we talked about some computational coding based approaches, some stats based approaches, but this last 40 minutes or so has really been getting a taste of what the applied nature of it is, and how you realize when you're in the problem, in the thick of it, you need to talk to the domain experts, you need to talk to the beekeepers, you need to talk to the law enforcement experts, you need to talk to the NGO. That a lot of this data is not without that context. And so I hope that was reinforced for you through this practice, and I hope you got to practice with the ideas of choosing what the appropriate statistical approach was. And I'm going to share back up in this last minute my slide 1 so you have my email address, share, so that if you want to reach out to me in the future, you want more information, and hopefully I can point you in the right direction. But I hope everyone had a good experience, and if there are any questions now, I'm happy to field a couple before our time runs out.